Assalamu alaikum, this is Saadat Nisar and I am teaching you this course on e-commerce. If you recall, in the previous lecture we had discussed the definition of e-commerce, then types of e-commerce. We had also discussed the definition of the internet and the World Wide Web. We reviewed the definition of the term HTTP, what HTTP protocol does, and what is the data contained in the log files, how can we make use of this data for certain useful purposes. In today's lecture, we want to see as to how the data can be transmitted across the internet. What is the communication mode prescribed for that? And if time permits, we'll also be looking at the topic IP addressing. Before we can understand the data communication over internet, it will be useful if we try to understand this concept on the simple networks. A simple definition of the term network is before you in this slide. A network can be anything from a simple collection of computers at one location connected through a connectivity media to the internet, which is a global network of networks. Then the term LAN or local area network. It is defined as a server-based network which is confined to a particular area or place. Most LANs, they consist of many clients and a few servers. In this slide before you, there is a simple LAN setup. You see there are 4 computers which are connected to each other. There are 2 client machines and there are 2 server machines. One is a network server and the other is a print server. Attached to the print server there is a printer. All these computers, they are connected with each other with the help of a networking device called a hub. The users, the clients on this simple LAN, they can make requests to the print server for printing purposes. These requests then are queued up or lined up by the print server, and accordingly on the basis of first come first served, these jobs are executed by the print server with the help of the printer attached therewith. The question is, why do we do networking? What is the benefit of it? Its answer is that we do networking because we want to avail the resources available on that network. Besides, we also want to communicate with each other, being users on that network. To give you an example, there are different types of resource sharings that can take place on the network. There can be file sharing, which means that there is a file server and a centralized place, a centralized computer where different files have been stored, and users sitting on that network, they can make requests for those files to the file server and they can then work upon those files. In this way, they can share this resource, these files available on the file server. Then the next type of sharing is hardware sharing. As I showed you in the previous example, in a LAN there can be a print server. Attached therewith there can be a printer, and users sitting on that network, they can make requests, the printing requests to the print server, who can then execute those print jobs on the basis of first come first served. Another type of resource sharing is application sharing or program sharing. This means that there would be a centralized server called application server on which there would be certain programs, certain applications residing, and various users on that LAN, on that network, they can make requests for these applications to that application server and then benefit from these applications or programs. We also do networking when we want to communicate, being users on that network. So there can be an email server in the network. On that email server, there can be accounts in the name of different users, and using their account, these users can then send email messages, they can receive email messages, and in this way they can communicate with each other. Now, all this communication on a network takes place because of network protocols. If you recall, I mentioned the definition of protocol in the previous lecture. Protocol means those set of rules or standards which enable computer machines on a network to talk to each other, to communicate with each other. In other words, it's a language using which computers can exchange messages, understand messages coming from each other. The information which a computer is transmitting to the other computer on a network, that information in fact passes through different intermediary layers, and on each layer certain specified protocols they operate, and before this information, this data is transmitted, is communicated to the connectivity media, these different protocols, they work upon the data and make it in a communicable format. There is a term called protocol stack. Protocol stack means the group of those protocols which operate on different layers, and they make the data in a format so that it can be communicated to the receiving computer, to the receiving device. In 1970s, there is an organization, an international organization called International Organization for Standards, or ISO. It proposed a conceptual model for network communications. This model is called Open System Interconnection Reference Model, or OSI model. It proposes a 7-layer architecture, and these layers are: number one, at the top there is the application layer, then comes the presentation layer, afterwards session layer, transport layer, then network layer, afterwards data link layer, and at the bottom is the physical layer. Data which is intended to be transmitted to a receiving device would pass through these several layers, or you can say these several stages, before it can travel along the connectivity media towards the receiving device. These layers are numbered from bottom up, so you can say that physical layer is the layer number 1 and application layer is the layer number 7. On each layer, these protocols, the certain specified protocols, they would play their role and they would leave certain instructions for the receiving side. Following those instructions, then the receiving side can understand what it has to do with the data. There is a term called encapsulation. When the data moves down the OSI stack, that is called encapsulation. From application layer, when the data travels through the physical layer, that process would be termed as encapsulation. The reverse of encapsulation is de-encapsulation. De-encapsulation means that when on the receiving side this data moves up the OSI stack, we say de-encapsulation has taken place. There is a term called header. Remember that on each layer, certain piece of information, certain segment of information is attached or affixed to the raw data. And this piece of information is called the header of that layer. Each layer except the physical layer has got its header, and the protocols which are designed to operate for such layer, these protocols then leave certain specified instructions on these headers. These headers are then removed on the receiving side. They are read on the same layers available on the receiving side with the help of the same protocols, and therefore the receiving side, because of these headers, is in a position to know that such and such message has been provided to the receiving side. It has to do such and such thing with this data, it has to display this data in this format, etc. You can say, in other words, that through these headers, in fact, the sender side has communicated with the receiving side. I can give you a candy bar example. You can assume that data is like a candy bar which has been wrapped in several wrappers, and on each wrapper there is instruction about the unwrapping of this wrapper, that how to unwrap this wrapper and what to do about it. In this slide before you, there is the ISO OSI model, and you can see on the left side there is the sender side, on the right there is the receiver side, and you can see the 7 layers: application, presentation, session, transport layer, network layer, data link layer, and at the bottom physical layer. You find the same layers on the receiver side on the right hand of the slide, and data from the sender side, after passing through these several layers, then through the connectivity media is picked up by the physical layer of the receiver side, and de-encapsulation takes place. Then all those headers which had provided certain instructions to the receiver side, these headers are read over by the protocols available on the receiver side, and in this way receiver side is in a position to know as to what it has to do with this data, and this data is in what format, etc. At the top you have found out that there is the application layer. This is at the top of the OSI model. It provides no services to any layer above it because there is as such no layer above the application layer. 2 very important protocols operate at this layer. One is the HTTP protocol, you are already familiar with this, and the other is File Transfer Protocol or FTP protocol. I'll give you an example. Say you want to move an Excel file on your computer machine, on the sender machine, to a remote server machine. Then with the help of this FTP protocol, you can do so. This file can then be uploaded on the server side with the help of FTP protocol, and the instructions that FTP protocol would leave on the application layer header, these instructions would be through the FTP protocol. Then the next layer is presentation layer. Presentation layer is regarded as the translator of the OSI model. This basically provides information or instructions to the receiver side about the format of the data. A very important protocol called MIME or Multi-Purpose Internet Mail Extension Protocol operates at this layer, whose job it is to define the format of the data which is being supplied by the sender side to the receiver side. For example, the MIME protocol would leave the instruction on the presentation layer header that this particular image is in GIF format. Therefore, the receiver side, please display on your computer machine this particular image in GIF format. Similarly, MIME protocol would also provide the information that this particular piece of text, this is in the HTML format. So please display therefore this information in HTML format alone. Then instructions about data encryption and data compression are also provided at this layer through the protocols. The next layer is the session layer. Data, after having passed through the application layer and then the presentation layer, comes to the session layer. At session layer, the set of protocols called Session Data Protocol Unit, SPDU, they operate and they provide information about the communication link between the sender and the receiver side. So you can say that session layer is for providing instructions about the communication link. There are 3 different modes of communication links. One is simplex. That means that communication between the 2 sides would be unidirectional. So only one side would be able to transmit the information. Then half duplex is the other mode. That means that communication can take place between the two sides, between the two directions. However, that cannot take place simultaneously. And third is full duplex. Full duplex mode means that both sides can communicate with each other. They can transmit information to each other at the same time. There is no problem about the transmission of data in this regard. Then at this session layer, there are certain checkpoints which are placed on the data stream. The purpose of supplying these checkpoints is to provide a mechanism so that the lost data can be retrieved. From the session layer, the data then comes to the transport layer. The transport layer has a very important function to perform. At this layer, two important protocols called TCP, Transmission Control Protocol, and User Datagram Protocol, UDP, they operate. You should know that data on the internet or on a network travels in the form of packets or groups. So it is possible that there is one packet in relation to an image, and say there are 8 or 10 text lines. For those text lines, there can be a separate packet. So all this job of converting the raw data into data packets is done by TCP or UDP at this particular transport layer. Besides doing this segmentation of data into packets, another very important function is performed at transport layer, and that is to regulate the flow control of data. I'll give you an example. Say you want to transmit certain data from the sender side to the receiver side, and the sender side sends 3 bursts of packets to the receiver side. Unless the receiver side acknowledge the receipt of these 3 packets, the sender side would not transmit any further packets. So Transmission Control Protocol, which is a very reliable protocol based upon this system of acknowledgements, functions here, and accordingly, first the acknowledgement is received from the receiver side that these packets have been received, and only then further packets are delivered by the sender side to the receiver side. I can give you an analogy. Say your connection is maintained with the receiver side throughout, just like a telephone connection. You make a telephone call and you are immediately receiving the acknowledgement, the feedback of the person you are conversating with. So in this particular case, the connection-oriented approach, your connection with the receiving side is maintained throughout, and you receive the acknowledgement from the receiving side, and based upon that acknowledgement, then you transmit further packets. On the other hand, the user datagram protocol does not follow this system of acknowledgements. You can say it is unreliable, therefore, and the analogy I can give you in this behalf is that as if you put a letter in a mailbox and you assume its delivery. You never get assured that whether this letter has actually been received by the receiver or not. So therefore, the unreliability of user datagram protocol arises from its inherent characteristic. From transport layer, then the data comes to the network layer. At network layer, a very important protocol, IP protocol or internet protocol operates, whose job is to provide the address of the sender machine and the receiver machine on the network layer. So therefore, what is the IP address of the sender and what is the IP address of the receiver? That information would be printed by the IP protocol on the network layer header. Another very useful, very important protocol called a routing information protocol works at the network layer. With the help of this routing information protocol, the routers, which is a device on the internet, this device has a very important role for the transmission of data from one point to the other. These routers, they create a routing table. And when the data packets arrive at a router, the router consults its routing table and discovers as to what is the shortest possible path through which this data can be delivered to the receiver machine. Afterwards, the next layer is the data link layer. At data link layer, these small packets of data, they are placed inside data frames. So this is one job of the data link layer, that it converts the data packets into data frames. Network interface card drivers, these particular protocols, they operate at this data link layer, which identify the MAC address of a computer machine. Now it's a new term for you. You'll hear about it further in a subsequent lecture. For the time being, I tell you, MAC stands for Media Access Code. So MAC or Media Access Code address is the hardware or the physical address of a computer machine, which is written on its network card. This address would not change unless you remove the network card and insert some other card having a different MAC address. Normally, this would remain as the same. Here I point out that your IP address is a different address from the MAC address. Your IP address is that 4-numbered address. When you are in a session on the internet, you are assigned a particular IP address for that session only. Your IP addresses, they are, for client machines, they are normally dynamic. So at one point for a particular session, you may be assigned a particular IP address, and say after 15-20 minutes you log on to the internet again and the ISP provides you a different IP address for that second session. On the other hand, I repeat, your MAC address, that remains the same most cases, unless you insert a new network card. The identification of this MAC address takes place at this data link layer with the help of protocols. There is also a mathematical calculation which is done on the data link layer, that is the cyclical redundancy check. This is used to confirm the integrity of a data frame. So therefore, a cyclical redundancy check would take place on the client side, on the sender side, and the same CRC would be done on the receiver side. If both these CRCs, these mathematical calculations, they match, that would confirm that the data frames, they have maintained their integrity. There is no change in the data frames. Next we come to the physical layer. This is the layer at the bottom of the OSI model. At physical layer, all the data information, including the header information, is converted into binary data. You must know binary data means ones and zeros. Ones and zeros is the language for the computers. Computers on the network view and understand each and every information in terms of ones and zeros or the binary data. So at physical layer, which has got no header, only the thing is that information is converted into binary data at the physical layer, and it results into the generation of electric signals or electric pulses. From the physical layer, therefore, the data would then pass along the connectivity media. It will travel along the connectivity media and would be picked up by the physical layer of the receiver side. So you can say, in other words, that at the physical layer of the sender side, these 1 zeros, these bits, they would be lined up, they would be queued up, and they would move along the connectivity media, say your copper cable, and they would be received by the receiving end. Now, let me tell you that these ones and zeros, or this binary data, they represent the on and off conditions of electronic circuits. Therefore, 1 represents the on condition of electronic circuit and 0 would represent the off condition of the electronic circuits. These ones and zeros, when they are received by the receiving side, then the receiving side, with the help of its protocols, would find out that this particular pattern of ones and zeros or electric pulses, this is related to this particular digit or this particular character, and this particular pattern, on the other hand, is associated with this particular digit or with this particular character, and accordingly those digits or those characters would be displayed by the receiver on its computer screen. So this is how the data from one point, the sender point, is received by the receiving side and is accordingly displayed on the computer screen of the receiving side. I want to take you through the OSI model again, so you can see before you in this slide the OSI model. The data on the sender side passes through the application layer, presentation layer, so on, up to the physical layer, and then from physical layer it travels along the connectivity media, is picked up by the physical layer of the receiving side. Then the data link of the receiving side reads the header provided by the data link of the sender side, and then it gets to know what instructions have been given to it by the sender's data link layer. The data link layer of the receiver then forwards this data to its network layer. The receiving side's network layer would read the instructions placed by the network layer header of the sender. Then from network layer of the receiving to the transport layer, here the transport layer of the receiving would come to know that it has to send acknowledgements because, say, TCP was used for the communication purpose. Then from transport layer to the session layer of the receiving side, here the receiving side would know as to what is the communication link about which the instructions have been placed by the sender's session layer header. From session layer on the receiving side, then the data travels up to the presentation layer of the receiving side, and the receiving side then come to know with the help of the MIME protocol that the presentation layer header of the sender side has provided this instruction, this information about the formatting of the data. For example, if the presentation layer of the sender has instructed that this particular image provided to you must be displayed in GIF, then the presentation layer of the receiver would come to know that it must then display this image in the GIF format. From the presentation layer, then the data goes to the application layer, and at application layer, the protocol of the application layer would read the instructions provided by the sender's application layer header, and therefore it would come to know whether it is an HTTP request or whether it is an FTP request, etc. So this is briefly the concept used by the OSI model for communication purposes on the networks. Interestingly, Internet does not exactly follow the OSI conceptual model. The Internet layers, they use the TCP IP stack, Transmission Control Protocol, IP protocol stack, which proposes a 4-layer architecture. In fact, this model was introduced in America by the Department of Defense before the OSI's conceptual model was contemplated. These 4 layers which are used in the TCP IP stack are named as, number 1 is the application layer, which is equivalent to OSI models application, presentation and session layer. Then the second layer on the Internet model is host to host layer, which is equivalent to OSI's transport layer. Third layer on the Internet model is the Internet layer, and this is equivalent to the network layer on the OSI model. The fourth layer is network access layer, which is equivalent to the data link layer on the OSI model. There is no physical layer as such in case of Internet TCP/IP stack. Rather, the task of conversion of data into binary takes place at the network access layer. I can show you the mapping of the internet model, the TCP/IP stack, with the OSI model. As this slide shows you, the application, presentation and session layer, they are equivalent to a layer on the TCP/IP stack where certain protocols, Telnet, HTTP, SMTP, FTP, they do operate. Then for the transport layer of the OSI, there is the other layer for the internet model where TCP and UDP protocols operate. For network, there is the internet layer where IP, RIP and ARP, these different protocols work. For the OSI model's data link layer, we have got a layer, the network access layer for the TCP/IP stack where network interface card drivers operate. So this was the mapping of the OSI model with the internet model or TCP/IP stack. Now again, there are certain protocols which have been listed before you in this slide. They are the TCP/IP protocol stack members. It can be useful for us to have a look on these protocols. HTTP, this is used for web page requests. You are familiar with this protocol. Telnet, also called Terminal Emulation Protocol. It connects a local computer with a remote computer. Then the FTP protocol or File Transfer Protocol. It provides an interface and services for file transfer over the network. So therefore, if you want to upload a file from a local machine to a remote machine, a remote server, or vice versa, this protocol can be used for that. SMTP, Simple Mail Transport Protocol. This provides email services on the internet. TCP, Transmission Control Protocol. This is a connection-oriented transport protocol, more reliable based upon a system of acknowledgements as we discussed earlier. Then User Datagram Protocol. It is a connectionless transport protocol, less reliable, no system of acknowledgement is used in it. IP or Internet Protocol. This provides basis for the IP addressing on the network. Then ARP or Address Resolution Protocol. This maps the IP address to MAC hardware address, and we'll have more discussion on this later. Then comes the RIP or Routing Information Protocol. This protocol is used for the making of a routing table, and then this table tells us what is the best path for packets on the network so that they can be delivered in an optimal fashion. Our next major topic is IP addressing. If you recall, IP addressing is that logical scheme which is used on the internet to address computer machines. So I gave you an example. For a particular session, each computer machine on the internet would have its unique IP address, which would be provided by the IP protocol. If I write 130.1.16.1, for example, that is an IP address. In this address, certain part represents the network address and certain portion represents the host machine on that network. So, and each part would be called an octet. The computers see this information as a data stream of 32 bits, ones, zeros. These are 4 bytes. 4 bytes means 32 bits. So computers on the internet view and understand this information in terms of 32 bits. Next, I want to show you this diagram. As you can see, there is a network, and this network is numbered as 140.57. The host machine is numbered as 220.200. This is in fact a class B type of network. I'll very shortly be telling you what is class A, B and C, etc. For this example, The IP address at the top, you notice, is 140.57.220.200, and in this IP address, 140.57 represents the network address, and 220.200 represents the address of that host machine which is sitting on this network, and it is shown on your diagram with the help of an arrow. So from this you may have understood that a network is composed of different host machines. The network address is different from the address of the host machines which compose that network. I'll be showing you a few more slides to elaborate this concept further. On the TV before you, getting the binary bits example is shown. There is an IP address 140.57.220.200. Remember that I told you that this information is viewed by the computers in terms of binary data, in terms of bits, that is ones and zeros. So you can see that 140 when converted to binary data represents 10001100. Similarly, 57 corresponds to a unique pattern of binary data. Then 220 has its own pattern of ones and zeros. 200 has got its own unique pattern of ones and zeros. This is shown before you. Just to recall that primary class mathematics for you, the slide before you shows how do we convert the number from decimal into binary. So we take the example of 57. So therefore, when 57 is converted into binary, we get 001111001. The two zeros at the beginning on the left side, they are placed because in order to complete the byte, which consists of 8 bits, it is compulsory that we put in some information, and by rule we place 2 zeros for the starting 2 places in order to complete our byte. Next is the reverse. When we want to convert the binary data back to decimal, the rule is that 2 raised to power 0 into 1 plus 2 raised to power 1 into 0 plus 2 raised to power 2 into 0 and so on. If we do the calculation in this fashion, we reach back to the decimal number, which is 57. Remember, for the purpose of calculation, we take the 0 at the left end as it is counted as 7, and the 1 at the extreme right is counted as 0. I repeat, for calculation purposes, we take the 1 on the right hand, we count it as 0, and we count the 0 on the extreme left as 7. And if we follow this rule, then we can convert our binary data, binary numbers into decimal. Next is, what are the classes of networks? The networks have been classified as A, B, C, D and E type of networks. Among these A, B and C, they are commonly used. They are for public purposes, whereas the class D and E, they are used for certain specialized classes. They are not for public use as such. The network number that starts with 0, we call that network to be A class. So in the slide before you, the minimum class A network is 0. That means that if the IP address starts with the bit 0, then it is A type. The maximum that can fit in the first byte is 127. We reach this figure 127 because if after putting in 0 at the first place, we maximize the byte by placing 7 ones, then if we calculate it in terms of decimal, we get 127. This is the clue, this is the basis from which we gather that 0 to 127 is the range for class A type networks. Class B type networks are those in which the first byte starts with 1 and 0. Therefore, after putting in 1 0, if we place further 6 zeros and we calculate in terms of decimal, we get the number 128. On the other hand, if we maximize this byte, after putting in 1 0, for the rest of the 6 places, if we place 6 ones and we calculate in decimal, we get the number 191. This provides us the clue, the information that range for class B networks is from 128 to 191. Then comes the class C networks. The class networks are those in which the first byte contains the digits 110 at the beginning. So following this rule, placing 110 in the beginning, if the remaining 5 places we place zeros, we get in terms of decimal as 192. This is the minimum number for class C network. On the other hand, if we maximize this by placing 5 ones after 110, we get 223 in decimal. This gives us the range of class C networks, which is 192 to 223. For class D and E networks, the rule is that they would start in the beginning by the digits 111, and if we make the calculation, then we find out the range for D and E types network is from 224 to 255. Remember that these networks, D and E type, they are used for special multicast and experimental groups. They are not for general public use. Okay, you may have realized one thing, that the minimum number that can be contained in a byte is 0, which means that there are 8 zeros in terms of binary in that byte. And the maximum number that can be contained in terms of decimal in a byte is 255, corresponding which there are 8 ones. So if on 8 places there are ones, the number in terms of decimal comes to be 255. We say 255 is the maximum number in decimal that can be contained in a byte. So 2 raised to power 8, which is equal to 256, 2 raised to power 8 or 256 different combinations of zeros and ones are possible in a byte. Next thing that I want to make clear to you is that for this classification into A, B or C type, we only are required to look at the first byte, the first number of the IP address. That is the basis through which we can figure out, we can identify that whether this is A type, this is B type or C type of network. So we have just calculated the ranges. We look at those ranges, we keep these ranges in mind, and therefore we can identify that this IP is A type, B type or C type. Next, I want to show you a slide which elaborates another rule which has been laid out by the experts. According to this rule, the class A network, which starts with 0, for class A network, the first number of the IP address would represent the network address, and the remaining 3 bytes on the IP address, they would correspond to the host machine on that A type network. So class A type network, which starts with the digit 0, the experts have laid down a rule that class A type network is the one for which the first number of the IP address would represent the network address, and the remaining 3 numbers or the 3 bytes would be allocated for the host machines on that class A type network. It implies that class A type network is a very large network. It can accommodate a number of host machines, millions of host machines. Class B type network is the one for which 2 bytes are reserved to indicate the network address or network number, and the last 2 bytes are for the host machines which constitute that B type network. Class B network, I repeat, is the one that starts with 1, 0. So if the first byte starts with 1, 0, we can immediately say that it is a class B network, and for class B network, 2 bytes for the network and 2 bytes for the host machines on that network. Next is class C type network. In class C type network, which starts in the first byte with the digits 1, 1, 0, the first 3 bytes are reserved to indicate the network address, and the last byte is for the host machine on that network. You may visualize that class B, where 2 bytes are for network, 2 bytes are for host machines, it is a medium-sized network. On the other hand, class C, where 3 bytes for network, 1 byte for host machine, is a very small network. And since 1 byte, the 4th byte is reserved to correspond to the host machine, therefore only 2 raised to power 8 or 256 maximum machines can be accommodated to build a class C type network. The question is that how many class A, B and C type networks are possible on the basis of information we have so far understood, and how many maximum host machines can be accommodated in each. So some calculations have been made according to which 126 class A type networks are possible, and each has the capacity to absorb or to accommodate up to 16 million host machines. That is very wide, very large network. In case of class B networks, the calculations show that maximum of 16,384 class B networks are possible, and each can accommodate up to 65,000 host machines on it. In case of class C networks, there are about 2 million class C networks possible, and each can accommodate up to 256 maximum host machines on it, which is a very small type of network. How do we reach these figures? How do we calculate these ranges? This is a topic that we shall be dealing with in our next lecture, inshallah. And for the time being, let's summarize what we have done in our today's lecture. We have basically discussed what is a network and how data transmission takes place over a network, what is the OSI model, what are the various layers, and what are the protocols that operate on each such layer, how the TCP/IP stack or the internet stack works, what are the protocols, what is the mapping of the OSI model with the internet model, and we have also reviewed one by one all these layers, application layer, presentation layer, session layer at a very broad level. And we have then started our new topic, which is IP addressing, and I have told you that IP address is that unique 4 decimal numbered address which is allocated to a client machine when a client machine comes over the internet, and this is the address through which the client machine can be identified. Let me repeat that each server machine would have its own IP address, a router would have its own IP address, a printer would have its own IP address on the internet. So the IP address understanding should be clear to you by now. We have also discussed that there are 5 types of IP addresses, A to E. A to C are the most commonly used for public use IP addresses, and I have told you that in class A, the first byte is for the network, 3 bytes for host machines, a very large network. Class B, which starts with 1, 0, 2 bytes for host, for network, and 2 bytes for host machines, a medium-sized network, and a class C network, a very small network in which the first 3 bytes are for the network address and the last byte is for the host machine on that network. This is enough for today. Inshallah, we'll be discussing our next topic, IP addressing further, and the domain name system, inshallah, in our next lecture. For the time being, Allah Hafiz. Assalamu alaikum, this is Saadat Nisar with the course on e-commerce. If you recall, we were discussing the concept IP addressing in the previous lecture. I told you that IP addresses are of 5 types, class A, B, C, D, and E type of IP addresses. Then I also familiarized you with the ranges. How do we calculate the minimum and maximum ranges in respect of class A, B, and C type of IP addresses? For public purposes, we are confronted with class A, B, and C type of addresses. D and E type are used for certain special purposes. I told you that in class A type, 1 byte is reserved to indicate the network address and the remaining 3 bytes are for the